Okay, everyone, welcome. Um, Today is the last day of classes in section, so that's exciting. So today I thought we'd just talk more about Fourier series, how to compute them, for example, do some examples, and then can leave with that. So there's no office hours for me this Monday. I mean, there's no office hours this Monday or next, but I may schedule some sort of office hours, I guess, during the last week during finals. Maybe not. But you're always welcome to email me with questions. And if it's like an elaborate question, we can set up a quick Zoom session. So yes, no quiz next week as well. But homework 12 is still due on Tuesday, as usual. Are there any questions people have? Any comments, concerns? Otherwise, we'll get right into it and compute some Fourier series. So let's do it. Let's compute Fourier series of the function, let's say it's going to be defined piecewise. So from negative pi to 0, and from 0 to pi, it'll be 0 and then x. Right, so it looks something like this, 0, and then it's x. Okay, so this is f. Okay, and we want to compute the Fourier series of this. So, right, we have a formula. Fourier series f sub x. It's going to be a0 over 2 plus the sum from n at least 1 to infinity an cosine nx plus the same things for bn. I guess you don't need to have 0 here because sine of 0 is 0, so those are just always going to be 0. Where an equals something and bn equals something. So let's see if you can fill in what an and bn are without me doing it first. So see if you can fill in what those formulas are. And then I'll fill them in for n at least 0. So why don't you work on that for about 7 seconds? See if you can remember the formulas. So remember how we got them as well. Right? They should be some formulas for orthogonal projections. Okay, so this equals 1 over pi times the integral of f cosine nx from negative pi to pi. And this equals 1 over pi integral from negative pi to pi of f sine nx. These are all with respect to x as well, the integrals. Right, remember just how we got this as well. Both of these were projection formulas, or coming from projection formulas. They're the inner product of f with, well, let me do it for, maybe for this one, the inner product of f with sine, and then dividing by the norm of sine, the norm squared of sine. Right, so the pi is the denominator, and this integral is the numerator. So that's how we got these formulas. Okay, so this is for all n greater than or equal to 0. These are the formulas. And this is the formula for the Fourier series. And so now we can just compute them. So why don't you start working on that, and I'll kind of work through it as well slowly. I'm going to do it on another page, so to make it a little cleaner, and then I'll come back to this page. So we want, I'll just copy what we have so far. Right, just to remember, here's f. And we have these formulas. So we'll do an first. And a good first thing to note is f even or odd, or both or neither? I mean, it can never be both, but is it even odd or neither? Because then you can use that to conclude that some of the coefficients are 0, for example. But in this case, f is neither odd nor even, so you're going to get both an and bn terms. So you can't, that won't help you here. But it's always good to note that, that way you don't have to do extra work. Okay, so let's just compute some of these. We have to split the integral into 2 parts because f is piecewise defined. So we should split it into negative pi to 0 plus 0 to pi. Right, but the negative pi to 0 part is the easiest part because that's just f is just 0. So this is going to be 0 times cosine of nx. Here will be x times cosine of nx. And so this is 0. So we can kind of just ignore this. So and just worry about this right term. It's 1 over pi. So this is all 0. Okay, and now we need to integrate x cosine of nx. So I think you'll probably be allowed a cheat sheet. I mean, well, it doesn't really matter. It's a take-home quiz or test for the final. But you know, it's a good thing just to like write down the formulas for the integral of x cosine or x squared cosine or something like this. Because in a Fourier series, I mean, if we ask you to do a Fourier series, you're probably going to have to compute some of these integrals. So if you just like have them written down somewhere, then when you actually, you know, write your answer down for your final, you can just then check that you got the right answer with your already computed integral. So it's a good way to check. Just kind of having a bunch of these formulas in the bank is often pretty nice to have. Okay, but we'll do it by hand right now. So we should integrate this by parts. So we have x sine nx over n. And yeah, the derivative of sine is, yeah, okay. From 0 to pi minus the integral of sine nx over n. So just integrating by parts here. Hopefully you're working along on your page as well. Okay, and now we evaluate this. So this term over here is going to be 0 because we're evaluating it at pi and 0, and sine of anything of any multiple of pi is 0. So we just get minus The integral of sine is negative cosine from 0 to pi. So we have 1 over pi, the negatives cancel, and now we can plug in pi. Cosine n pi over n squared minus cosine 0 over n squared. Okay. And just to make things a little easier, let's factor out this n squared. Okay. And now let's rewrite this. So cosine of 0 is 1. And now let's figure out what this term over here is. Okay, so we said last time that a convenient way to write this is negative 1 to the n. Right, so let's just check that this is correct. So if n is 0, then this is cosine of 0 should be 1. So if you plug in 0, you should get 1. You do. If n is 1, you get cosine of pi, which is negative 1. And when you plug in 1, you get negative 1. And so anytime you plug in an even number, you're going to get 1 for cosine up here, but then you're also going to get 1 down here. And so these are equal because cosine of multiples of pi oscillates. Great, so you actually notice that you can also write this, if you want, as 1 over pi n squared times a piecewise function, depending on when n is even or odd. If n is even, then this becomes a 1, minus 1, you get a 0. And if n is odd, then this becomes negative 2. So another way to write that. But you could just keep it in this formula if you'd like. So any questions on this computation? Hopefully I didn't make any mistakes as well. Okay, now we can go back and plug that into our formula. So 1 over pi n squared, so we get n is 1 over pi n squared, negative 1 to the n minus 1. We should actually so we actually should have done 0 separately, just to make sure we get the right thing. Because sometimes, right, we're dividing by n here, so we should really do a0 separately. A0 is 1 over pi, the integral of f dx, because cosine of 0 is 1. So we get 1 over pi, negative pi to pi, which is integral from 0 to pi of x dx, 1 over pi x squared over 2 from 0 to pi. So you get pi over 2, right? Because the reason we should do a0 separately is you can also see it here. I mean, if I try to plug in 0 for n, it's just it's undefined, right? So it's because it's a different number, right? So we find pi over 2 for a0. So we should also write that down, pi over 2. Or I'll do that over here. Okay, and then now we need to figure out what Bn is. So we do the same thing. Okay, and now we just do the same computation. Here we don't need to do B0 separately because, I mean, if you just plug in B0, you're just always gonna get 0, right? You get negative pi to pi, f sine of 0, and this is just 0, and so this is just going to equal, you're always going to get 0. So you don't really need to do this. Okay, so now we integrate by parts again. It's negative. Is a negative. Oh, this should also be 1 here. Okay. So it's often nice on your final, for example, to do all these computations in a neat, like, sectioned off area to kind of, and if you mess up, maybe just scrap that paper and use another paper, because you really want to make it as, as easy to follow as possible. And so let's plug in pi. And then when you plug in 0, you're just going to get 0. Okay, and then you get the integral sine x over n squared from 0 to pi. Okay, and now you can evaluate this. This is -1 to the n. And this is just 0, always, right? So we get -1 over n, -1 to the n, which is, I guess you can rewrite that as 1 over n times -1 to the n plus 1. Okay, and then we've solved for our coefficients. All right, and then you can now wrap this up as one Fourier series. So there's a couple ways to write the final answer. If you want, you can drop the sums and just do a bunch of, you can just plug in certain values of n, and then just, you could do you could just write it as pi over 4 plus the coefficient of cosine x. So I guess, or you can keep it as a sum. Here, I'll do both in a sec. There's a question. Can you go over why you do A0 and B0 separately again? Yeah, so I don't actually need to do B0 separately. That was the point, because you're just always going to get 0 for B0. Always will get this. You don't need to do B0 separately. In fact, there is no B0. If you look in the formula, this is n greater than or equal to 1. So there really isn't a B0. But the reason you do A0 separately is because if I try to, this is the formula for AN. Here's, this is the formula for all n, for n at least 0, right? And when I try to compute this formula, at some point I'm going to divide by n, right? Which is incorrect if n is 0, right? It can't divide by 0, right? Just for the simple fact that the integral of cosine nx, you'd like to say it equals sine of nx over n, but this is only true n doesn't equal 0, right? If n equals 0, if n equals 0, then this equals the integral of 1, which is just x, right? So, and you can't just evaluate this integral at n equals 0 to get x. It just, they don't equal each other. And so, well, I guess you could try using L'Hopital's rule, but it's not going to get you the right thing. So, so you really need to do it separately, as we found out, because our A0 is pi over 2, but if we were to try to plug in n into our n equals 0 into our formula, you just get infinity. That doesn't make sense. So that's why you need to do A0 separately. Okay, so writing our final answer, we get pi over 4 plus some n at least 1 And then you can basically just copy this in. Cosine nx plus sum n greater than or equal to 1, 1 over n, negative 1 to the n plus 1, sine. So this is a perfectly valid formulation. You can also say, since this term oscillates between 0 and 2, then you could write this sum as like n even, or I guess n odd, because the even terms are 0. You could do this. There's so many ways to write this formula. So when n is odd, you get negative 2. And then you can keep this the same. Or if you want, you can just drop the sums and write them all out as an infinite series. So you could do pi over 4 plus negative 2 over pi cosine x plus negative 2 over pi. Or I can even factor out the negative 2 over pi. Plus 1, 3 squared is 9, cosine 3x, plus 1, 25 cosine 5x, plus dot, dot, dot. And then you can add the sine terms. Sine x plus negative 1/2 sine 2x plus 1/3 sine 3x plus, right? Sorry, I ran out of room here, but you could write it out just an infinite series without the sums and do like these dot, dot, dots once it's clear what the pattern is. So any of these are valid answers. So any questions on this example? If I made a mistake, please let me know. I don't want to perpetuate the mistake. Okay, if there are no questions. So what shall we talk about next then? We can do another Fourier series example. Let's do another one where we have to extend a function, where we want a Fourier sine or cosine series. On a quiz, would we be given one whole question like this? Seems extensive. Well, maybe not on a quiz, but on an exam, yeah, on the final. You could definitely be asked this. You could, on a final, you might be asked something like compute the Fourier series of a function. And then you might also be asked to compute the Fourier series of the derivative of the function or something, and have to use some theorem. So for example, let's do another Fourier series. Let's compute the Fourier series of this function. F of x is 0 and 1 from negative pi to 0 and 0 to pi. This is there. Quick question, is the function x sine nx odd or even? Let's figure that out. Let's put that, let's add another page. Would it get any, so let me answer that question in a sec. Let's work on this one. So is it odd or even? Well, is x odd or even? X is odd. Is sine of x odd or even? This is odd. And so the product of two odd functions is what? this should be even. Just like the sum of two odd numbers is even. A good way to figure out as well is an even function means that f of minus x. So if you have an even function, your function looks something like this maybe. So if this is x, minus x should be the same value. And if you're odd, f of minus x, if you're odd, you look something like, you know, like this is an example of an odd function. So x and minus x means your value should be negative of what it is. And so a good way to check is just to plug that in. If you plug it into here, you get negative x sine negative nx, and then this thing becomes, it can be brought out because sine is odd, so the negatives cancel. And this is f of x, so this means f is even. Okay, so another question, would it get any more difficult in these types of problems? Not too much more difficult, hopefully. I mean, we don't really want to test you on your ability to integrate. We would like to test you on your ability to reason about linear algebraic concepts. So hopefully it won't be too much more difficult. We don't want you to do heavy integration. But for example, I mean, there's only like a limited number of easy examples you can do, and so you can kind of just know them, and that'll be nice to have in the back of your mind. For example, like let's say we want to compute this, where is it? The Fourier series of this function. So this function looks like 0 and then 1. Well, we could just compute the Fourier series, like exactly like we did from the previous example. We can just compute the coefficients. But an easier way is, now that we have the Fourier series for, I'm going to call this something else so we don't get confused. Let's say G. Now that we have the Fourier series of f, where f was previous, f was 0 and x, we don't need to integrate to compute the Fourier series of G anymore. Because what's the relationship between f and G? Right, we see that G actually equals just the derivative of f, except it's at 0, because G of x equals f prime of x for x not equal to 0. So almost everywhere, except for finitely many points, since the derivative is not defined at 0, it's the derivative, right? And so we have this theorem that says basically if the function and its derivative satisfy some nice continuity properties, then the Fourier series of G is just a term-by-term differentiation of the Fourier series of f. So I'll write that out. If f comma f prime satisfy some continuity properties, if you're actually going to use this theorem, you're going to want to say exactly what these are in the statement, but you can find them in the book. What we really need them is to be what's called piecewise continuous. And I guess their derivatives are also piecewise continuous. Which these are. I mean, basically what that means is, like, is it almost continuous except for like finitely many points? Then yeah. So anytime you invoke a theorem, you want to make sure that it satisfies the correct assumptions. So make sure you actually, if you're to write this on an exam, to actually state the proper assumptions and check them. But in this case, they satisfy some continuity properties. Then Fourier series of f prime equals the term by term differentiation of Fourier series of f. So you can just take the Fourier series of f. So for our example, we should find that the Fourier series of g, being the derivative of f, should just be, let's just take the derivative. Let's look at our Fourier series. Sorry, I went back a page. We look at our Fourier series of f, and we can just differentiate each term with respect to x. So, right, we look at each term here. Let's see. So this is a single term right here. We can just differentiate this, and those will be the coefficients. Do we need f double prime to be piecewise continuous? Yes. That's what sorry, I meant the derivatives of those functions need to be piecewise continuous. So the derivative of f prime is f double prime. So I'll just write that out again. So f double prime. Okay, so yeah, you just take the derivatives. I guess I already lost what they were. Sorry. So the coefficient of sine will be n times this, and the coefficient of cosine will be n times this. So n times 1 over pi n squared. And the coefficient of, there, I already lost it. -1 to the n plus 1. Yeah, I think that should be good. So this is like, I think you can find this, the exact conditions, I think you can find in theorem 4, I believe. Yeah. Theorem 4 in the book says exactly what you need. Well, actually, you need to be 2L periodic, 2 pi periodic. But you can just extend it to periodic. Okay. Where were we? Okay, so are there any questions so far? Oh, there's a negative sign somewhere. Yeah. Any questions? Okay. Well, I mean, that's most of Fourier series. I mean, if you can compute a Fourier series, I think you'll be pretty good for the exam. Yes, I believe so. Although, actually, let me check real quick. Because actually, if I remember correctly, you need to be what's called periodic. So why don't we just actually like check? Let's just actually compute the Fourier series. I mean, there's one way to check. This one might actually be wrong. Let's just check. Let's just compute the Fourier series of G by hand. This will be another practice. So G was this function. It was actually done in class, or in lecture, I think, at some point, or maybe even the book does it. But we can just do it out. So this one's not as bad. AN is 1 over pi, integral from negative pi to pi. So these are all, again, from 0 to pi now, because this is 0, of cosine nx. And Bn is 1 over pi, integral from 0 to pi, sine nx. And then you should do a0 separately, 1 over pi, 0 to pi of 1, which is 1 over pi x from 0 to pi, which is 1. Yes, okay. I did make a mistake somewhere. Okay, so let me correct this. This is incorrect as I stated, but we can fix it in a sec. Let's just finish computing these. So you get 1 over pi sine nx over n with a, yep, that's fine. This is 1 over pi cosine nx over n, the negative sign. This is 0. This is have we done this right? Yeah. And this is negative 1 to the n minus 1. Okay, so yeah, I did make a mistake somewhere. So my bad. There's a crucial, so right, we see that we get 0 for the an terms, for the bn's we get this, and a0 we do get a constant term, which is 1. If I did everything correctly here. So we did not find that, right? This, we got the sine term right, the bn's, that was correct. But this was not correct, and we also had a constant term, right? So what it gives, so I did make a mistake. There's actually a crucial assumption here. This is very crucial, I guess, that I missed, which is, and it was called 2 pi periodic. So let me go over what that means. But that's pretty crucial because now actually this is not true. So this is our, I'll fix this and say our counterexample. There we go. Now everything's correct. It is a counterexample. The Fourier series of G is not this. It's a Fourier series of G should be what you get from here. So you get 1 plus the sum -1 over pi n, -1 to the n minus 1, sine n pi nx. Okay, and the reason is because the reason you can't differentiate term by term is because f is not 2 pi periodic. So this is theorem 4, by the way, if you want to look at in the book. What this means is that if you go to f, 2 pi periodic means that at pi and negative pi, these should be the same value. So I'll write that over here. Say f is defined on negative pi to pi, then f of negative pi, I believe you want that to equal f of pi for it to be 2 pi periodic. So, and since f doesn't satisfy that, you can't use theorem 4. So actually that was kind of a tricky problem, because the term by term differentiation is not correct. So good thing we did that example. Okay, so with that in mind, yeah, let's do one more example where we do odd and even extensions. Let's compute what's called the Fourier sine series, for example. So it's not just the Fourier series, but it's a sine series, which means we only want sines in it. And let's do it of f of x, which is defined to be, let's say, x on, let's just make it even easier, which equals 1 on 0 to x, or 0 to pi. So it's only defined on 0 to pi. It equals 1. Okay? And we're going to define the Fourier sine and cosine series. Okay? So the way you define the Fourier sine series is if you only want sines in your Fourier series, then that means your function, which is defined on negative pi to pi, must be odd. And so what you do is you consider an extension of this function, and you extend it from negative pi to 0 so that it's an odd function. Which means for us, we want to consider the function where we make it the extension, we'll call it f odd, will be defined now from negative pi to pi piecewise. Oops, and it'll be the same thing it was from 0 to pi, but from negative pi to 0, we're going to make it -1. And this makes it odd. And we can do the exact same thing to do an even extension. So it's going to be 1 from 0 to x to pi, and then from negative pi to x to 0, we want to extend f so that it's even, because then the Fourier series of that extension will only contain even terms, so it'll only contain cosine terms. So to make it even, we just extend it like this. Okay, so this would be 1. And now the Fourier sine series of f is just, by definition, the Fourier series of f odd. And likewise, the Fourier cosine series of f is by definition the Fourier series of f even. Yep. And that's how you just get a series for a function with only sines and cosines. It'll approximate the function, so the sine series will approximate the step function using only sines. And so in particular, it'll approximate this red section using only sines. And the Fourier cosine series will approximate the constant function 1 using only cosines. So in particular, it'll approximate this red section using only cosines. Right. So I mean, you can talk about the Fourier series of the Fourier sine and cosine series will be defined from negative pi to pi. But if you're only interested in values between 0 and pi, then if you want, you can restrict your domain to 0 to pi. But you can still define the Fourier series everywhere. So yeah, in particular, for example, let's say you wanted to evaluate, evaluate or approximate, I don't know, f of pi over 2 using only cosines, then what you could do is you could extend f to be an even function, find the Fourier series of that function, and then since it's continuous or piecewise continuous, it converges at pi over 2, for example, and you could just plug in pi over 2 into your cosines, and that's just a an infinite series. I mean, f of pi over 2, it's 1, but that would give you an infinite series where you have 1 equals some infinite series, where you've plugged in pi over 2 into cosines. So why do the equations hold? Is it just definition? Yeah, I'm kind of defining this Fourier sine series for you. This by definition, I'm saying the Fourier sine series is the Fourier series of the odd extension. And then I guess you can restrict it again to the domain that if you'd like, or you can only consider points between 0 and pi. And I'm defining that the Fourier cosine series is the Fourier series of f even. Is there a reason/proof that when we want a Fourier series for an odd function, that we don't get any cosines? The reason/proof is just when you try to compute them. Let's say f is odd, and let's say you want to compute an, which is the integral of f cosine nx from negative pi to pi. And then you can just reason why this has to be 0, right? This is odd. This is even, which means together they form an odd function. And an odd function integrated from negative pi to pi is going to equal 0. Yeah. So that's always nice when you have odd and even functions, because then you don't need to compute half of the Fourier coefficients. Some of them will just automatically be 0. Okay, so I think I'll end there. We went over how to compute Fourier series, how to compute the Fourier series of a derivative. You need some properties. So you should really check these. If you're ever going to use this on an exam, you should just be careful that it satisfies the correct properties. We were not careful, and that's why we got the wrong answer. But if you're ever uncertain, you can always just compute the Fourier series like we did. Usually the integrals are not too hard, so you maybe have to do an integration by parts here or there. And then we talked about sine and cosine series by odd and even extensions. Yeah, and that's about it.
Jeremy, I have a quick question.
Yeah.
Will we be having like a review in our week?
I don't believe so. I mean, I don't think Nikhil has planned any sort of review. I don't have a review set up. But I mean, I may hold like a office hours or so the week after or during our week.
Okay, thank you.
But you're always welcome to email me if you have questions.
Sure.
Yeah. All right, well, I'll be on for a little longer if you have any other questions. Otherwise, enjoy the last bit of the semester.